Let's do one last difficult problem here with some conversion of energy and working back and forth with formulas. So it says a 125 kilogram boulder falls off a cliff and strikes the ground going 12 meters per second. How much energy is dissipated when it hits the ground while coming to rest? And then finally, how high was the boulder before it fell? So let's get a little diagram of what's going on here. I'm going to draw my cliff and my boulder. And I know this boulder is 125 kilograms and it's going to fall. And we know that when it strikes the ground, right at ground level, the velocity is 12 meters per second. So let's just think through the problem here. We know that this thing starts from rest with some energy due to gravity, and then it falls. And just as it hits the ground, all of the kinetic energy gets all of the gravitational energy gets converted to kinetic energy just before it hits the ground. Now, if my question is how much energy this thing has, I'd like to calculate the gravitational energy, but I don't know how high the cliff is, so I can't use my formula for E equals mgh because I don't know the h. In fact, that's what I'm supposed to find out. So we're going to have to work this a little bit backwards. Let's find out how much energy it had from its kinetic energy if we can. And I know that formula is 1/2 mv squared. And I do have the information to find that. I have a mass and I have a velocity. So let's go ahead and find out what that is. So that's 1/2 times 125 kilograms times 12 meters per second, quantity squared. And when I say quantity squared, that means that the 12 gets squared, but the units also get squared. So I'm going to go ahead and do the numbers here. 12 squared is 144 times 125 times 1/2 gives me 9,000. And then I end up with kilograms times meters squared per second squared. And again, kilogram meter squared per second squared is joules. All of that energy is going to get dissipated when it hits the ground. Now, in order to find the height that the ball was before it fell, I got to work backwards and say, well, all of this kinetic energy came from gravitational potential energy. And since I want to know how high that thing was, we can refer back to a formula that we wrote down and used earlier. We just simply rearranged this equation and said height is equal to the energy divided by the mass times gravity. You'll have to pardon me, I skipped a step here. Let's go ahead and write down what we had. We knew that the mass was 125 kilograms and the velocity was 12 meters per second. And I always know that gravity is, again, 9.81 meters per second squared. But to keep it simple, we're going to use 10 meters per second squared. And then we were supposed to find the energy. We were supposed to find the height. So we already solved energy. Let's go do that height part of it right now. So I have my 9,000 joules divided by the mass, which is 125 kilograms, times gravity, which is 10 meters per second squared. And just simply working through the numbers, I get 9,000 divided by 125 times 10, so 9,000 divided by 1250, and I'm going to get 7.2. And this is a mess of units here. So again, let's go over and let's just do a little work in the margin or at the bottom just to make sure that we got the right thing. If I have a joule divided by a kilogram times meter per second squared. All right, we agree that a joule was a kilogram meter squared per second squared. So I'm going to substitute that in, and I've got a kilogram meter squared per second squared divided by this, which carries down, divided by kilogram meters per second squared. So now again, kilograms cancel, second squared cancels. Now I have meters squared divided by meters. That'll cancel this meter and leave a regular meter there. And sure enough, 7.2 meters is a unit of height. So if we know the kinetic energy, we can find out that that boulder fell from a height of 7.2 meters.